Okay, let's continue with our topic of discussion or topic under discussion, which is the Thevenin and Norton equivalent circuits. Okay, so when I introduce this topic, we use this circuit with three sources as an example. And I stated that we are trying to determine the optimal value of R6 to fit within a certain spec, right? And the purpose of performing this Thevenin and Norton analysis was to determine the optimal values. So we have to find three quantities. We look at the circuit from the perspective of R6. We remove R6 from the circuit, and then we analyze the circuit three times independent of each other to find three quantities: VTH, RTH, and IN. Thevenin voltage, Norton current, and Thevenin resistance. The relationship between all three quantities is given by Ohm's law. That is used to verify our answers at the very end. Okay, we do not use Ohm's law to find any of the other quantities directly. There is a reason for that. And I will come back to that once we get done with Thevenin resistance. Okay, so just a summary here. What we are doing is we are trying to find the Thevenin and Norton equivalent circuits for any kind of load in the circuit. Load in this case is basically the component that is under analysis. Okay, and in our example, it is R6. In electrical engineering, anything that supplies energy is a source. Any component that receives energy is a load. I believe I mentioned this on the first day or the second day of class, and we are going over the terminology. Okay, so again, anything that supplies energy is a source. Anything that receives energy is a load. In our case, we only deal with resistors. Okay, we are only analyzing resistive circuits. So we only determine Thevenin and Norton circuits for resistors or resistive circuits. That is what the chapter is, chapter 2, resistive circuit analysis. Okay, resistors are linear. Okay, the voltage and current have a linear relationship. Hence, the circuit comprising of resistors are also linear circuits. We only determine Thevenin and Norton circuits for linear circuits in this class. We are not looking at anything else. That's the second point. And the third point is any one-port linear network, which is all the circuits that we're looking at in this class, can be represented by its Thevenin or Norton equivalent. Okay. So again, these are just some minor concepts. They do not affect our analysis in any way or our application for Thevenin and Norton theorems. Okay. This some things to keep in mind. As I said, it does not actually affect our course right now, because the only thing we look at is linear one-port networks in this class. Did you have a question? Okay. All right. So these next two slides cover everything. Again, this is not a new analysis technique. You're simply applying the analysis techniques to determine the Norton and Thevenin circuits. Okay. So three analyses summarized right here in points 6, 7, and 8. And then, of course, at the beginning, these are just some things that I actually tell students. I noted it down here. Usually, I do not have a wall of text in my slides, but these two slides are very important. And so I've noted it down so that students don't have to. Okay. Three quantities. Again, remember, three quantities: voltage, current, and resistance. So we have to perform three separate analyses. Okay, three separate analyses. Any circuit that you're given, you will analyze three times if you're asked to find all three quantities. And all three analyses would be independent of each other. They have no bearing whatsoever on the other two quantities. So if you analyze a circuit for Thevenin voltage, then that circuit for Thevenin voltage has nothing to do with the circuit for Thevenin resistance or for Norton current. you would take the original circuit, CKT, by the way, is my acronym for circuit, and you would analyze it 3 times. Thevenin voltage, Thevenin resistance, and Norton current. All 3 are independent of each other. Okay, so you're going to redraw the circuit 3 times. And when you redraw the circuit, each circuit is different from the other 2. Okay. The first quantity I usually recommend to students is to find Thevenin resistance first, because that's the easiest. Okay, or easiest or straightforward, if you will. Again, this is something you have already done. You have done this at the beginning of this chapter. All you're doing is you take the original circuit, and I'll put this inside a box. And of course, R6 is removed from the circuit. I'm still sticking with the example from the previous slides. And this was out plus and out minus, right? Out plus and out minus. So when you remove R6 from the circuit, you're left with an open pair of terminals where nothing is connected. Those are your terminals of analysis. Okay, everything that you do, everything that you measure is done at those 2 terminals. And so the first one is measuring Req between those terminals. Req between those open terminals. Again, you remove that component from your analysis and you look at the circuit from the perspective of that component. In this case, you're measuring Req, the total equivalent resistance between those terminals, which is something you have done before, right? You reduce a large network of resistors down to one single resistance. So the way to do that, well, in real life, it's easy. You just take a digital multimeter and you put it on ohm meter mode and you measure the resistance between those terminals. Theoretical analysis, you have the sources in the middle. So the only way to reduce it down to one single resistance is to eliminate all the sources, or technically reduce all the sources to 0, which is something we learned last week. You reduce all the independent sources in the circuit to 0, meaning you replace a voltage source or all voltage sources in the circuit with a short circuit wire, and you replace a current source with an open circuit, or you simply remove it from that circuit. So now, after you do that, you redraw the circuit, and all you're left with in the circuit is a bunch of resistors. And if it is reducible, you reduce it down to one single resistance. If it's not reducible, well, then we cannot use this technique to find RTH. And that is why we need to find VOC, or Thevenin voltage and Thevenin resistance, and then we apply Ohm's law to determine RTH that way. But for the most part, the circuits that you would encounter in homework, in quizzes, and in the exam will be reducible. Okay, so you remove all the sources from the circuit, take all the resistors that are left, reduce it down to one single resistance between those analysis terminals, and that's your Req. That is your RTH, or your Thevenin resistance. Let's take a 10-second pause. Think over that. Let me know if you have any questions. Again, not a new analysis technique. It is simply the application of a previous analysis technique. But you should be aware of, well, you should be aware and know how to set up the problem correctly. In this case, the problem setup would be you would take the original circuit, remove all the sources or reduce them to 0, and then you analyze for REQ. Straightforward, right? So the most modification is only done for Thevenin resistance. Voltage and current, the Thevenin voltage and the Norton current, they don't require much modification. The only thing that happens at the output terminals. So we have our original circuit, right? What I'm going to do is, again, represent it as a sealed box. I have 2 terminals coming out. This is R6. Again, R6 is not part of the analysis. We have already removed R6 from our circuit. Out plus, out minus. There's actually no modification done from this point on. Once we remove R6 from our analysis, all we are doing is we analyze this circuit with any method you choose, any method you want, whether it's mesh current analysis or node voltage analysis, and you find the open circuit voltage between those 2 terminals. See, once you remove R6 from the circuit, the terminals are open, hence open circuit. You measure the voltage, well, measure if you are trying to do it in real life, you would measure the voltage at those terminals. Theoretically, you would calculate the voltage at those terminals, and the voltage that you obtain is your open circuit voltage, Thevenin voltage. So again, not much to modify in here once you have removed R6. That's it. Again, not a new analysis. It's simply the application of your analysis. Now, in an exam, I might specifically state, find the Thevenin voltage using such and such a method. Then it's testing 2 things. It's testing for the students' knowledge of setting up a problem for Thevenin voltage, plus it tests or assesses a specific analysis technique. If no technique is specified, as in the homework, you can choose whatever you wish to use. You can use superposition, you can use mesh current, node voltage, whatever you wish. If it has only one source in there, you can reduce it down to one single resistance and apply series parallel analysis technique. Apply any technique you want. And then you find the voltage at the output. All right, any questions? Yes.
A question like that might be find the by.
Yes. Yeah. So I'll come back to that point once I'm done with all 3. Point number 6, make sense? Okay. Point number 7 is the same thing, except what we do is we place a short at the output terminals in order for current to flow through. So we have our output terminals. We have R6. Again, I'm just drawing R6. You don't have to. This is just to illustrate the explanation. Okay. You don't have to draw R6. Out plus, out minus, and I place a short circuit wire between the two terminals, and I note or calculate the short circuit, the current flowing through that short circuit. Hence the notation ISC, short circuit current between those terminals, and that would be my Norton current. So REQ is RTH, VOC is VTH, and ISC is Norton current IN. Okay. If you note VOC and ISC, reference direction typically is taken with plus at the top and minus at the bottom, and ISC hence will always go from top to bottom. It'll always be going downward. Now, it may be that when you finish your analysis, you might obtain a negative value. In that case, the only thing it means is that polarity is flipped and the current direction is also flipped. That's all it would mean. But if you see the current direction as opposite of the polarity, then there's an error in your calculation somewhere. Okay, if you get an answer, both would be negative, depending on the polarity and the reference direction shown here. So either you get both positive or both negative, but one cannot be positive and the other cannot be negative. Current always flows from high to low, plus to minus. So if VOC has a plus up top, then the current would always go in the downward direction. So if you obtain a positive value for VOC and a negative for ISC, one of them is wrong or one of them is incorrect. Okay, small thing to just keep in mind. But again, the two circuits, the only difference is VOC is measured between the output terminals, open terminals, and the current, of course, needs a pathway to flow through. So it's flowing through the short-circuited terminals. So the circuits are different. They may look very similar, but the effect of that short circuit could be very large. Okay, that short circuit would take out everything in parallel with it. Again, it's a short circuit. So if there's a resistor or two resistors in parallel with that short circuit, they are now all eliminated. Anything in a parallel with a short circuit is effectively removed from the circuit because all the current will be going through that pathway. So again, the analysis would be different for each circuit independently. Once you find RTH, RTH has no bearing whatsoever on ISC circuit or VOC circuit, and vice versa. Let's take a 10-second pause. You think over that. Let me know if you have any questions. Any questions at all? Yes. No, that applies to all three values that you determine at the end. So we can use Ohm's law as verification at the end. Obviously, if you're doing this in real life, we can find two quantities and find the third, which is what we do for RTH. So if RTH, in the end, it turns out that all circuits are not reducible down to one single resistance. Most circuits are complicated. We cannot find REQ that way. So the only way to find Thevenin resistance is to find the Thevenin voltage, find the Norton current, and then apply Ohm's law. V over I would give you the Thevenin resistance. Circuits that we see are reducible. So sometimes some professors like to teach a shortcut saying that you find the Thevenin resistance, find the Thevenin voltage, and then apply Ohm's law to find Norton current. I don't teach that in my class. I would specifically ask all students to determine all three quantities And then you verify your answer by applying Ohm's law. That makes sense, right? Okay. All right, so we are out of time, but I just want to point out, take a look at the Thevenin Norton homework. I will go over this circuit next class, but again, it's rather straightforward. Again, you know what you need to do. So take a crack at it and then see if your answer matches up with what I do next class. All right. So we'll end class here today, and I will review these 2 slides again before beginning next class. If you have any questions, I will be in my office today, tomorrow. I'll also be available via Zoom if you need. All right. We'll see you on Wednesday.